Good morning, my good students. This is Dr. Eddie Morgan over at Clovis East High School. Today we're going to look at the second part of lesson 8.4. We're going to apply our knowledge of exponential functions to the concept of compound interest, one of the places you'll have the most use for this in your life. Our first slide is vocabulary, and we simply want to differentiate between compound interest and simple interest. Let's stop with simple interest, the second one. Simple interest means that you only pay interest on the principal. If you borrow money, you're only paying interest on that money. Whereas compound interest, you pay interest on the principal plus any interest you've already earned or already been accrued to your account. In other words, suppose you borrowed $1,000 from somebody and said, they said you're going to pay me 10% interest each year. Well, 10% of $1,000 is $100. So it means at the end of the first year, you'd pay them $100. At the end of the second year, you'd pay them $100. The third year, you pay them $100. You're just paying the interest each year. Compound interest is different, though. In compound interest, the first year goes by, and now I owe you my $1,000 plus 10%. So now I owe you $1,100. So the second year, though, when I go to pay, I owe you $100 on the principal, but I also owe you 10% of the $100 that was the interest last year. So you see that ends up to be another $10. So now, what I owe the interest on the second year is not $100, it's $110. And each year it gets bigger and bigger because you're paying interest on the principal and on the interest it's already. Now this next slide shows the formula for compound interest. Now at first it looks rather complicated. The thing that makes it so complicated is that often when you're dealing with banks, compound interest isn't figured every year, it's figured every month. However, or even every day, but the interest rate is annual. So if you look at the letter N in these, they refer to the number of times it's compounded per year. So like if you do it every month, N is going to be 12. And what happens then is our normal, if you remember, our normal equation says y equals a times b to the x. Well, a is the principal. That makes sense. But notice our rate is going to be dependent upon how many times we do it per year. In other words, if we did it just once a year and n was 1, then b would be 1 plus r, which is what we used to say before. It's 100% plus the rate. And our t would simply be 1. But when you do it multiple times in a year, you end up having to have this formula here. In other words, my growth factor here is 1 plus the rate divided by n. So in other words, that means that my rate's 10%, but I'm going to do it 12 times during the year. Then I take the 10% and divide it by 12, and that's where the r over n comes from. Likewise, when I count how many times I do it, instead of doing it once a year, if I'm doing it 12 times a year, then it's going to be 12 times t. So it's kind of complicated, but if you work with it a little bit, you sort of see how it's related to a simpler one. Now let's look at a problem that illustrates compound interest. In this problem, it says that you decide to invest $2,000 in an investment that earns 6% interest. It's compounded quarterly, that means 4 times a year, and they want to know how much will the investment be worth in 5 years. Well, let's write down our equation first, principal, and then our growth factor is 1 plus r over n. Again, it's the rate, my annual rate, divided by how many times I'm going to do that in a year. In this case, it'll be the 6% divided by 4. And then how many times am I going to apply it? Well, I'm going to apply it 4 times each year times 5 years. So P, our principal, is 2,000. The rate of interest is 6%. N is 4 because quarterly means I'm going to do it 4 times a year. And I want to know how much it'll be worth in 5 years. So there's my equation. Again, look at it carefully. It's not as complicated as it looks like. My growth factor, 1 plus 600 divided by 4. Again, 6% is my annual rate, but I'm going to do that 4 times a year, so I don't charge 6% each time. I charge 1/4 of 6%. That's where I get this 0.6 divided by 4. That's what I charge each time quarterly. Likewise, how many times am I going to do this? 5 years, but I'm going to do it 4 times every year, so 4 times 5. So let's simplify it. And we have 2,000 times 1 and 15 thousandths to the 20th power. So we break out our calculator. Remember what our calculator key looks like, either the caret or the x to the y or the y to the x formulas. So we're going to put in 1.05 caret 20 equals, and we get that number there. So we multiply, and now we're going to round off to the nearest penny because we're dealing with dollars and cents. To the right of 1 is a 0, so that's not old enough to go to school, so we drop it off. And we'd say in 5 years, that $2,000 will be worth $2,693.71. I want to share with you an interesting story about how wealth is made in our country. It's about saving for retirement. It's a story that I borrowed from a class I took on financial peace, and it talks about 2 twin brothers. Ben, one of the brothers, starts saving $2,000 a year at age 19, but then when he gets to be 26, 7 years later, he stops saving and never saves another dime. But he's put the money into an investment at 12% return. His twin brother Arthur does, at first he says, "Oh, I'm too young. I don't have that kind of money. I need all my money." So he doesn't put aside money at first, but he's watching his brother save from 19 to 26. And finally, when he's 27, he says, "You know what? I'm going to start saving too." Well, in other words, he starts putting $2,000 a year into a retirement account when his brother stops, but he keeps doing it until he's 65. So you got to get this. The first brother started at 19 and put $2,000 a year when he was 19, 20, 21, 22, 23, 24, 25, 26. So about 8 years. His other brother then starts saving after his brother stops, and he puts in $2,000 a year from 27 to 65. So in other words, for the next 38 years, he puts $2,000 in. So one brother puts in $2,000 for 7 years. The other brother puts it in for 38 years. Who do you think is going to have the most money at the end of retirement? Obviously, one brother put in a lot more than the other. So I'm going to show you a graph on the next page that'll kind of give an indicator of where this goes. So this is a very interesting graph. Notice the yellow is Ben. He's the one who started at age 19. He started putting $2,000 away each month in a fund that's growing at 12%. But then you notice where the arrow is here under the box. It shows that when he turned 27, he stopped putting money in, but the amount of money he's put in, that 16,000 is still growing at 12% per year. And by the time he is 65, you see that money that he put in just 7 or 8 years is now worth $2,288,996, even though he didn't put any more money in after he was 27. On the other hand, his brother Arthur is the blue. Now, at the point at which Ben stops putting money in, that's when he starts putting money in. So he's putting money in, and it's the same account. He's growing 12% per year. And yet, when he gets to be 65, even though he's put in a lot more money, he's only worth $1,532,000. Still a lot of money, okay? But still, notice that even though Arthur has actually put in more money, he hasn't put it in for as long as a ton. And the lesson to be learned here, of course, is the sooner you start putting money aside for retirement, the longer it stays in here, the greater the exponential curve causes it. So you see, a little money at the beginning of your life invested is worth a lot more than as you get it. The problem with a lot of people in our culture is most people don't even start thinking about retirement until they're like 55. And you can see if you back it up here, how much does the curve grow in 10 years? Well, not that much. So it's about time when you're doing investment. So let's look at another example. And this time, instead of investing, you're borrowing money. For your first year of college, you borrow $5,000 at 6.4% interest annual rate. How much will you owe after 6 years if the interest is compounded annually? Now, the fact that it's annually is going to make this a lot easier problem. So $5,000, 6.4% interest in 6 years, but annually. Why does it make it so easy? Watch what happens when n is 1 annually. My principal is $5,000. My rate is 6.4% or 64 thousandths. N is 1 because I'm going to do it once a year, and I want to do 6 years. So look at my formula. Notice that when I do it annually, it's 0.064 divided by 1, and that's 1 times 6. So when you put it together, it just looks like our simple y equals a times b to the x power. So in other words, if you have a problem and it's annual compound, it becomes very much like the problems we did in yesterday's assignment. So once again, let's get out our calculator, use our exponential key. 1.064 caret 6 equals about 1.450. Multiply it by 1,000, round off to the nearest penny, and you see at the end of 6 years, your $5,000 you borrow, you owe them $7,254. Okay? So when you borrow money, that interest is compounding and it's getting bigger and bigger. So when you borrow money for college, you want to pay it off as soon as you can. In the next problem, we want to look at each of these for each of the following. What is the growth factor or the decay factor? Well, and then decide what's the percentage rate of growth or decay. Kind of working backwards is something we did yesterday. So in the first one, I noticed that the key thing is what is b? A times b to the x. B is 1.05, and that's greater than 1. So that means this is growth, 1.05. What's the percentage rate of growth? Well, think of it as taking the 100% off of it. So 1.05 minus 1 means that this is a 5% growth. On the next one, our factor is 0.95. Now in this case, 0.95 is less than 1, so that makes this decay, and the decay factor is 0.95. So how much is it going down each year? Well, think if it started at 100%, what is it now? It went down 5%, so this is 5% decay. See, in the first one, how much did it change from 1? It went up 500, so it's a 5% growth. Here it went down 500, so it's 5% decay. On the next one, 87 thousandths is less than 1, so we have a decay, and that's our decay factor. Each time we're multiplying by 87 hundredths. What is the decay rate? Well, take the 1 and subtract the 0.87. How much did it go down by? It went down by 91.3% decay. Okay? So notice that went down a lot, practically gone. In the next one, pretty simple. 15 is greater than 1, so that's a growth, and the factor rate is 15. Well, again, how much did it go up from 1? Started at 1, so it's going up by 1,400%. All right? Kind of hard to see that maybe, but you think 15 minus 1 is 14, and in terms of growth, that's 1,400%. The next one, E, our growth rate is less than 1, 71 hundredths, and so my decay rate, 1 minus 71 thousandths, is going to be 92.9% decay. Again, quite a bit of decay there. So let's look at the compound interest one more time, kind of a little enrichment here. There's our main formula. A equals the principal times the quantity 1 plus r over n to the n minus t. Now notice, if I compound annually, you see that n is 1. This equation basically breaks down to the interest is the amount earned is the principal times 1 plus r to the t power. Pretty simple exponential. If I do it 4 times, then it's 1 plus r over 4, and then we do it 4 times each year times the number of years. And if I did it annually, it'd be 12. Let's look at what a difference that makes in our next slide. So problem 12 says you want to invest $10,000 in an account that earns 5% interest. You have the option of having the interest compounded annually, quarterly, or monthly. How much money will be in your account after 20 years? Which option earns the best money, the most money? Why? So let's take a look and try it with each formula. Okay. So first, if I do annual interest, I'm only going to do it once a year. So it's simply 1 plus the rate. So that's 10,000 times 1 plus 0.05 to the 20th power. And that's going to be 10,000 times 2.653, or after 20 years, my $10,000 has become $26,532.98. Let's look at quarterly. Now I'm going to have the 5% is going to be divided by 4 and done 4 times a year, and it'll be done 4 times 20, 80 times. Okay, so when we do the calculation here, we end up with 10,000 times 2.701, or $27,014.85. So you can see by doing it quarterly, we ended up earning $1,500 more than we did it if we did it annually. You can see a pattern here. What you think if they do it monthly is going to be 12 times. So we put in 5% 12 times a year, 12 times 20. And as we do the calculation, notice that now we've gone up another $100 from that. So obviously, the more they compound the interest, the more often they do it during the year, the more that it grows. And so if you have a choice, if you're putting in an investment, you would like them to compound it as much as possible. Some banks actually compound interest every day. In would be 365. On the other hand, if you borrow money, you'd like them to compound it annually because it won't grow as big. But that's what compounding can do for you. So compounding the interest monthly earns the most money because the interest is earned more often. All right, guys, keep well and be safe out there.